Our group is focused on the characterization and analysis of radiation effects on semiconductor technologies. I'm Elaine Greer.
I'm Isa Valdez.
I'm Herman Rodarte.
I'm Munir Tuvel.
I'm Gaith Ayub.
There are several industry applications where semiconductors are exposed to ionizing radiation. Examples would be devices that help aircrafts go to space or create imaging from CT scanners. Our project focuses on characterizing ionizing radiation effects on semiconductor technologies to find a technique that won't damage the devices during fault detection.
The goal of this project is to optimize inspection methods for semiconductor devices exposed to damaging cobalt-60 gamma radiation through understanding laser effects, characterizing radiation effects, and developing testing protocols. IV sweeps of STI diodes were performed pre and post gamma ray exposure to measure damaging effects.
Laser-assisted device alteration is an imaging technique that helps with determining where a potential fault is on the device. The device that undergoes LADA will be exposed to a 1064 nanometer wavelength that will generate a localized photocurrent on the device to alter its characteristics. Depending on how much these device characteristics change from the original value will determine if the device passes or fails.
STI diodes were fabricated on a FOXFET wafer using lithography, trench etching, mask removal, and oxide deposition. Radiation creates traps at interfaces, increasing surface recombination and generation current. A laser generates electron hole pairs in the depletion region, and the resulting current is measured as these charges move.
IV sweeps were performed using a device analyzer with a diode's gate, drain, and body held at 0 voltage. While the laser was eliminating the diode, the source voltage was swept from 0 volt to 3 volt.
These were the equations used to find the concentration of interface traps. The left two equations were used to find the generation rate of electron hole pairs. The middle equation was used to find the surface recombination velocity. And finally, the last equation was used to find the concentration of interface traps.
Data from the IV sweeps was plotted pre and post radiation at 0.2 and 0.4 watt laser powers. Increasing power to the laser increased the photocurrent magnitude by increasing generation rate, while exposure to gamma radiation increased photocurrent by increasing the number of trapped charge sites. Lastly, as shown on the right, radiation permanently altered the device characteristics, while the laser only temporarily changed it. Graphs and equations from the previous slides were used to calculate trapped charges due to radiation, showing higher trapped charge concentrations in SRV at lower laser powers due to higher trap activation at the surface.
Radiation caused permanent damage for forming traps at the Si-SiO2 interface, detected through increased body current. This fault detection method improved device reliability, yield, and performance.